Okay, video number 2 in polymers. What we're going to do is look at some reactions that can occur with ethene to make it into different monomers to then make it into different polymers. And these different polymers are from the last syllabus chapter, the syllabus dot point. Let's find it here in yellow. We talked about polyethylene and how it's an addition polymer. And we'll also talk about now polyvinyl chloride, polystyrene, and polytetrafluoroethylene, PTFE. We'll talk about how those are made. Let me just scroll back through. And also remember that we've got to come back to that question because I put it in the wrong spot. Okay, so many other addition polymers can be made by substitution reactions on the ethene monomer before the polymerization. Okay, so for example, Teflon here is made from the monomer back here, tetrafluoroethene, or it's got the ethene backbone, but instead of the 4 hydrogens, it's got four fluoros, therefore the tetrafluoroethene. Okay, and we need to talk about how we get from there to there. What we can do is a substitution reaction. So we can take our ethene and we can do substitution reactions with fluorine gas to produce the tetrafluoroethene, then do a polymerization reaction, and we get a very different polymer. From polyethylene, we get something called polytetrafluoroethene, or PTFE, and it's called Teflon. That was its like registered kind of marketing name when it was first made, I think back in the 60s. Okay, you can also do, instead of doing that, you can do substitution reactions with chlorine, and you can substitute out 1 hydrogen for 1 chlorine to make chloroethene, or its old name, vinyl chloride. I don't know why. And what you can do is then polymerize vinyl chlorides, do an addition reaction, and you get polyvinyl chloride, or PVC. Okay, what you can also do in the third one that we need to look at, we can do a substitution reaction with benzene. We can put a benzene ring on the ethene backbone there to make ethanol benzene. Its old name is styrene. And then what you can do is a polymerization reaction. Now, that benzene ring, remember, is very unreactive and stable. It just stays as benzene rings, but you get addition across the ethene part. So you get polystyrene. So you get a long chain with benzene rings hanging off it. Okay? We'll talk about a bit more about those in a little bit. I felt that this was a good time to talk about names. Polymers are usually named by putting the prefix poly before the name of the monomer. Okay? So it's not technically the name of the polymer. We use poly and then we use the name of the monomer, okay? However, as I've said before, older names are often used for these monomers. So, the polyethylene is the name of the polymer of the ethene monomer, as the old name for ethene was ethylene, okay? So, even though polyethylene only has single bonds in it, so it's kind of like an alkane, we still call it polyethylene because we're saying it's the poly of the ethylene monomer, okay? It doesn't have double bonds in it, even though there's an ene there, and the poly tells us that, okay? We can recognize it as an addition reaction that started from a double bond and is now to a single bond. So it's important to recognize that the name refers to the monomer and not the polymer. The ene suffix given to molecules that contain a double bond, but the polyethylene does not contain double bonds, only single. That's a bit confusing. It's probably not the best way, but it's the way that we've got to learn. So, the proper chemistry wizards, the IUPAC, the monomer is named ethene, but the polymer is officially named polyethylene. So, another name for ethene is ethylene. That's not the proper way to call it. And the other name for polyethylene is polyethene. That's not the way that they're saying to call it. They're saying that the proper way to call it is to abide by their rules for the monomer, but well, abide by their rules for the polymer as well, but to use the old polymer name. I don't know. Okay, so back to Teflon. PTFE, polytetrafluoroethene. So the monomer is tetrafluoroethene. Look at that, it's ethene but with 4 fluorines instead of hydrogens. And what you get is an ongoing polymer, and when you put it in this notation, big brackets or square brackets, the N afterwards, and then the single carbon-to-carbon bond with the fluorines, 4 fluorines around there. So nothing happens to the fluorines, but we get rid of the double bond to a single bond. Properties. So the chains of these, the PTFE, line up together with lone pairs on the fluorine atoms, okay? You get 3 lone pairs on them. And they repel each other, okay? Yeah, these repel each other, and a strand close by can repel each other too. And so they each form temporary dipoles. So the dispersion forces exist between successive chains. Because fluorine is so electronegative, the electron concentration is highest on the outside edge of the chain, around the outside, and it increases dispersion forces. So Teflon strands stick together really, really well. High melting point of 327 degrees Celsius, very high tensile strength as well. Okay. Uses non-stick surfaces on cooking equipment. So non-stick surfaces, basically. So cooking equipment is most commonly where we come across it. Also coatings. Coatings, if you put Teflon in there, it becomes stain resistant. Stuff doesn't want to stick to it. It sticks to itself preferentially. Okay, so stain resistance coatings. I'd say the paint industry has started to use it as well in there. I know recent paints that they've really got a kind of water-based repellent technology where it doesn't really stick at all. Might be something else. Could be Teflon in there. I'm sure in the early 2000s they went through a marketing phase where like, now with Teflon. I'm sure they did. I'm sure they would have got on that bandwagon. Fabrics and carpets coated in Teflon, making them stain resistant. Also artificial body parts, because resisting other chemicals from getting to whatever's underneath. And also, it's believed that it's non-toxic and you can put it in your body. High-grade electrical insulation, plumbing and pipe thread sealant. So if you've ever done a bit of plumbing, you'll notice that really thin, it's called tape, but it's not sticky, that really thin white stuff that you wrap around there, like threads around the male end of the thread before you tighten up in the female, and it creates a seal in there. That's Teflon tape. Yeah. Okay, enough about Teflon. It is an addition polymerization because you're going from a double bond between that ethene backbone to the single bond. So another type of addition. Another addition is PVC. What happens there is we do an addition reaction with the ethene to put a chlorine on there, and this is called chloroethene, or the old name vinyl chloride, and therefore when we polymerize it, we get an addition reaction. The double bond is now a single bond, bonding to other monomers near it, and we form polychloroethene, or polyvinyl chloride is the correct name. I should swap them around. So the base unit is 2 carbons, the 3 hydrogens, and the 1 chlorine on every second one. So repeating, chlorine on every second one. Remember 4 fluorine, so it's just fluorine, fluorine, fluorine. No hydrogens on the Teflon. Here we're going to have a chlorine on every second one. Okay. So PVC properties. Not only has dispersion forces between the chains, but because of this chlorine and the angles, you also get dipole-dipole interactions. Okay, because that is a polar bond there. Okay, so you get dipole-dipole interactions between strands. So it's a high tensile and rigid polymer, and it's amorphous in chain interactions. Okay, uses for PVC. Second most produced synthetic polymer after polyethylene. Wide variety of applications. Piping from plumbing, PVC piping. You think of the plastic piping used in plumbing. That's PVC. Automotive parts as well. Roofing, exterior building surfaces. Yeah, high tensile strength, rigid polymer. Perfect for that. Okay, polystyrene. So, ethanol benzene. We get this ethene backbone with a benzene ring. I realize that's skeletal, but it's the benzene ring sticking off there. And what ends up happening is with addition polymerization, it's not going to affect the benzene ring. It's very stable, unreactive. You're just going to get additions across that ethene backbone. So here you get your single bond between the carbons. Sorry, between here. Single bond between there, whether there was a double bond, and you get a repeating unit. So every second carbon is going to have a benzene ring sticking off it. Every second one. Okay? It's important because those type of questions come up in the HSC. Every second one. So properties, no polar bonds. We got only carbon to carbon or carbon hydrogen bonds here. So the chains do not have dipole-dipole interactions. But the benzene groups can line up between successive chains. They can approach each other, and they have significant dispersion attractions between them. The benzene ring restricts orientations. It stops it from turning so much. Okay? And so polystyrene tends to be clear, hard, and brittle. It doesn't want to flex. It doesn't want to turn because of those benzene rings. Polystyrene has many uses. You might recognize it if you're old like me. CD cases. Food containers as well, polystyrene, and also plastic cutlery. Okay. Usually widely mated. Okay. So polystyrene, but usually what muggles call polystyrene is actually polystyrene foam, like that packaging material. You know the stuff. I haven't put an image here, but that's called EPS, expanded polystyrene or styrofoam. Styrofoam was the brand name of the company who originally made it. You can see where the name came from, but that extent. So when they do the polymerization reaction, they bubble air through it, and it gives it this kind of amorphous, kind of bubbly structure. That's kind of very lightweight, but kind of strong and good for packaging. So making cells of the polymer with air in between. Low density material, great insulation properties. That's why you see it in the polystyrene cups. Commonly used in food and beverage containers and housing insulation. Yeah, and also that packaging material too. Food and beverage containers. It was really big. A lot of polystyrene was used in the 1980s. Yes, I was around back then. A lot of food containers, like fast food containers, not that it was as big back then, but the one that comes back to me is McDonald's always had their burgers come in polystyrene containers. And what ended up happening was that these polystyrene containers, because they ended up out in the environment, because people weren't as good at looking after the environment back then. So polystyrene containers were everywhere. And it was also kind of studied that they weren't breaking down, that they weren't... they were sticking around, and so there used to be all these campaigns that that polystyrene container will last 1,000 years. And it was kind of the first stage, not the first stages of the environmental movement, but very, very early stages in there. So polystyrene has kind of a bad name because of that. It was one of the kind of wake up to the plastic kind of pollution kind of thing. Lots of kind ofs in there. Okay, I thought that I'd add polypropylene into this mix here. It isn't in the syllabus point, but it's very easy to understand, and it's very likely to come up. Okay, so your monomer here is propene. So you've got a double bond in there, but it's pro, so you got 1, 2, 3 carbons. So just a single bond up here. So it's like an ethene backbone with a methyl group. Okay. Think of it like that when you're talking about polymerization. So what you do when you get addition on there is you get the 2 base units from the ethene part, but you get a branch, a methyl branch. And that methyl branch will be repeated every second one, okay? And so that's polypropene. Okay, properties, no polar bonds again, because we've just got carbon-to-carbon or carbon-to-hydrogen bonds. So no dipole-dipole interactions. So the macroscopic properties of polypropylene can be manipulated by changing the arrangement of the methyl groups coming off the chain. I'll talk about that more, but we can put that methyl down the bottom, okay? Polypropylene is used for large molding that needs structural strength, such as piping furniture and, wheelie bins and stuff like that. That's all polypropylene. And if you think of the plastics, it's that plastic that kind of has a slightly waxy feel when you feel it. It's still smooth, but it's not as smooth as like PVC or polyethylene. It has that kind of slightly waxy feel. All right, to finish up addition reactions, I've got a couple of past HSC, or a few, but we need to go back. Remember that one I put in here by mistake? This one here. Okay, we've got ethene, we're doing something and we end up with a polymer. Which of the following compounds represented by X in the flowchart? Okay, so what can we do to ethene to then make it into a polymer? Okay, not cellulose. If we react ethanol across the double bond, it's going to be an addition reaction and we're going to get ethanol. And we can't polymerize ethanol, so it's not that. And it's not glucose, we'll learn about that more, but what we can do is, it's talking about doing a substitution reaction to make it into styrene, and then to do it a polymer. So it's talking about taking that ethene precursor, making it into styrene, or that double bond with the benzene ring, and then polymerizing it into polystyrene. That's why I put it too earlier. You needed this. What an amateur. Anyway, here's one that I hope is in the right spot. So question 11 from the 2003 HSC. Which polymer is made by the polymerization of methyl methacrylate? Okay, we haven't studied that, but here's the monomer, okay? Now, when I look at this monomer, I see a double bond, and I go, oh, double bond, and it's a monomer. Oh, and it's going to a polymer. Okay, so it's likely to be addition reaction, and if it's addition polymerization reaction, it's going from a double bond down to a single bond. Okay, so if this is your monomer, and it's the only monomer, and it's addition, it's not going to have any more double bonds in it. And so when I look at A, I see that the double bonds are in there, and I go, no, go away, it's going to have single bonds. Okay, B, C, and D all have single bonds. Okay, so what we've got here is three different options. Okay, we've got three different backbones here. To help identify the backbone, what I'm going to do is start with my double bond. I've got to redraw it. Okay, I'm going to redraw it like that, and then I'm going to draw whatever's coming off it as branches, because this is what is reacting, nothing else. Okay, so on the right hand side I've got a methyl branch coming off. That's this one here. And down the bottom underneath I've got a COOCH3. That's not going to be part of the reaction. And on the right hand, on the right hand side, on the left hand side, the other right, I've just got two hydrogens coming off it. Okay, so I've just redrawn the monomer to really focus on what's part of the reaction and what's not. These are not changing at all. Okay, so what's going to happen is you're going to get a ongoing polymer. I'll just do a backbone there. Let's start here. You're going to get hydrogen, hydrogen, and here you're going to get a methyl, and here you're going to get your COOCH3. Okay, and then it's going to repeat. You're going to get your hydrogen, hydrogen, and then your methyl, COOH3, CH3, and then you're going to get your HH. So you're going to get that kind of thing happening. Let's see if we can recognize it here. Okay, look at D. D has left out this, okay? D's left out. The carbon, the every second carbon with just the hydrogens on there. So that's what they try to trick you with. They've left off every second one, so it's not that one. Look what they did with this one, okay? They've got the backbone here, and they're showing that there's this chain coming off at every second one. No, that's not right. Look at this one. They've written that as CH2, and then they're showing this every second one. So every second one is a CH2, which is good. And then every second one, not opposite to that, every, words, you got a methyl branch, and then you got your COOCH3. So the answer is B for that one. Should I highlight it? B. Okay. Notice how with this type of problem, what they do is they rely on your knowledge of how addition polymerization works. They give you an unknown monomer, and then they give you choices of polymers that it could be. It's a good type of question, and my strategy would be do what I did there. Redraw it centering around the double bond, and then put the branches coming off it and know that the branches are not going to change. Okay? All right. Here's a more general one. A student created following models to demonstrate a chemical process. Okay, it's hard to see in black and white, but you can kind of get the gist. Okay, got something there, and we've got ethenes. Okay, something's going on, and we've got a main long chain of ethanes. So we're going from, it's a polyethylene process. So what they've done is, here's the initiator, and so it sticks at the end, and then it's finally terminated and it's stuck at the other end. So that's the initiator. So what's the chemical process being modeled? Addition polymerization is probably all they're looking for that 1 mark. But it's actually polyethylene, if we want to add it a bit more, just to make sure. Why are models such as these useful? Why are models useful at all? Okay, not part of this topic, but we use models to show changes in reactions and to visualize angles, bond angles, atom types, and changes in molecules. Why are they useful? Human brain is visual. Okay, it also allows us to see and hints at properties or intermolecular forces. I think that's probably what they're looking for. That's what I use models for. Oh, I'm zooming in. Go away. Okay. 2017, question 12. What is the product when propene undergoes addition polymerization? Let's draw propene. Meth, eth, prop. Let's put the ene in there. And so we're getting the hydrogens. Oh, hang on. What am I doing? A hydrogen down here. Oh, I should rub that out so it's not confusing. A hydrogen down here and a CH3 up there. So when you get addition polymerization, notice that we're starting from an ene. We would be going down to an ane. So any of these with a double bond should be gone. Double bonds in there, go away. Double bonds in there, go away. Okay, single bonds, good. Single bonds, good. Okay, well, now let's look at that. The double bond's going away, and we're going to form a carbon backbone. And on one side it's going to have a H and a H, and on one side it's going to have H and a methyl. And then it's going to repeat. H, 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 methyl. H, H, H methyl. Okay, it is D. Okay, look at B. There's no methyl branches there. And what have we formed? This is polyethylene. Okay, so that's if ethene undergoes, we get B. Okay, so it's not B. It is D here. We've got one methyl branch coming off every second one because it was only on the second one. All right. So here's one from 2018. Draw the structural formula for vinyl chloride and its polymer, polyvinyl chloride. Okay. Vinyl chloride, remember, was the ethene, where you do a substitution reaction and you get one chlorine on there. So it's actually, if you want to be like, vinyl chloride, you're talking about chloroethane, you dag. Okay, so that's the old name, vinyl chloride. So polyvinyl chloride, okay, square brackets, square brackets. What's it going to form? Well, the double bond's gone down to a single on the left-hand side. The hydrogens haven't reacted, and the chlorine and the hydrogen hasn't reacted. N. Okay, to show it's an ongoing one, and those ones going on. I'm sure that if you drew an ongoing chain, something like this in there, and did your H's right and your Cl's right, you know, that type of thing, I'm sure you would have got the marks. They're not that nasty. Have I done it right? I'm sure you would have. Alright, I don't think I'm going to go through this one. Describe the steps involved in the process of addition polymerization and explain the uses of polyethylene and polystyrene in terms of their structure and properties. Okay? Brief outline. So the steps involved, so you need to talk about your monomer and your conditions to get polymerization. You could even use polyethylene for an example there where you use an initiator in addition to go on. That's probably what I'd do. Okay, explain the uses of polyethylene and polystyrene in terms of their structure. I would draw their structure out, a little bit of it, and then talk about the intermolecular forces. Then talk about the properties, and look, uses, and then go on to uses, okay? Start with the chemistry. Talk about how the structure of the chemistry will give the whole thing certain properties, and then because of those properties explain the uses of it. Alright, that's enough for this one. The next video, as you can see, is going to be about copolymers. I'll see you next time.